that graph that we drew before should be perfectly fine if we relabeled it as W0 and W1. It's more of a conceptual tool to get you thinking that there's sort of two ways to visualize spaces. You can visualize how data points are actually being separated with your classifier, or you could picture how things behave in your weight space. And we'll sort of see there's like a duality between the two ways of thinking. Let's move on to another example. So here, this is just another sample data set. In this case, it's representing the logical AND function, but that's not too important. And I guess this is just potential practice for writing out what the inequality constraints will look like. So for example, for the very first equation, we want W0 x0 plus W1 x1 plus W2 x2. That has to be less than 0 for equation for this one. And the 0 terms go away, so we're just left with W0 is less than 0. So you can just do this as an exercise later to figure out what the constraints are and if there's like a possible setting of the weights that satisfies this equation. So for example, from before, there's a whole bunch of different lines that will satisfy this equation, right? So if we had a classifier that looks like this, it's going to perfectly separate the 2 points. In this case, we have 4 points, so we'll have a few more constraints, but you should still be able to find settings of W0 through W2 that can satisfy the constraints.
Since we all have a 1 on x0, so why don't we start over?
Sorry.
Like,
oh,
x0
yeah.
is not changing, so why do we have it there?
Yeah, I guess even if x0 is not changing, I guess x0 sort of serves the role of the bias here, so you can shift everything potentially by.
Which bias are we talking about?
For the rest of this lecture, we're only using the bias as in the intercept bias. Yeah. But I guess in general, we're not going to be using this method of explicitly finding out what the classifier is by hand. This is machine learning, so our goal is to try to learn this through data and find what the weights should be. Right, okay, so there's some terminology here that's important to note. So we call data linearly separable if there exists a linear decision rule that can perfectly separate the two examples. And in general, we have this idea of a hyperplane, which is essentially the generalization of aligned higher dimensions. So in 2D space, we had for this constraint perhaps that W transpose X equals 0, and that's our decision boundary. In higher dimensions, you can imagine X and W are n-dimensional vectors. That's going to be some plane that passes through the origin. And this is always going to pass through the origin if we set it equal to 0, because when you set X equals to 0, then it passes through the origin. And yeah, okay, should be good. We can also visualize the knots in weight space. So I think this is a more accurate drawing of what I tried to sketch before with W0 and W1 placed on their more logical locations. So each of these specifies a constraint, and the overlapping constraints specify a feasible region where that's where your weights have to be selected from to separate the two examples. And we have a few more terms here. So the problem is considered feasible if the feasible region is non-empty, and a feasible region is a region that satisfies all the constraints. So when it's linearly separable, that means the feasible region is non-empty as well. Another concept here to note is that when we're visualizing stuff in the weight space, each training example, rather than being a point, it instead specifies a half space that the optimal weights or the feasible weights must lie in. So like, this is what we were doing before, right? Like we were numbering each of the data points, and each of the data points corresponds to an inequality, which you can think of in weight space as specifying our optimal weights have to lie in the set of the hyperplane. Yeah.
What do you mean exactly by half space?
Yeah, a half space is an inequality constraint with a line, a linear condition on one side, and then a constant on the other side. So I guess this is something you can learn more about in convex optimization potentially as well. We probably won't test you on like vocab specifics like this, but conceptually you can just think of like a half space is like splitting this 3D volume into two spaces. So we have one half space on one side and the other half on the other side. Okay, so we can also, in higher dimensions, it's going to be hard to generalize this visualization. We generally can only picture things in 2 dimensions. So the way to get around that is when you're working with 3-dimensional data and you want to picture something, then you picture it on a 2D slice. So for instance, if you looked at the AND function, you can consider the case where x0 equals 1. So if we fix the feature value to be equal to 1, what does the decision boundary data space look like? And you can also do the same thing with the weight space. So you can fix one of the weights if you wanted to picture what was going on. But in general, I guess like visualizing high dimensional data is like a hard problem, and the only real tool we have is like to try to project things into lower dimensions or try to slice things in a way to picture them better. Yeah, so if you wanted to check your answers on the previous problem, I guess they're all here as well. So you can check that the inequalities you derive match up to the ones here. Okay, any questions on this like initial conceptual visualization of what decision boundaries look like? All right, so we're gonna now work our way up towards the logistic regression loss function. And along the way, we'll sort of define some loss functions that don't quite make sense. We'll point out problems with why they don't work, like for optimization reasons or for some other reason, which will help motivate why logistic regression is defined the way it is. Okay, so so to motivate logistic regression, we generally want to learn the problem. So we want to learn the weights. And the reason that's the case is if it turns out the data is not actually linearly separable, then there's no default optimization way to solve the problem. So if you gave a convex optimization solver a problem where it's not linearly separable, it'll probably get stuck or return not a number answer or something like that. So to deal with this, we will instead try to use a machine learning approach where we try to define a loss function and then optimize the loss function using gradient descent. And this is generally what we use in practice because real data is usually not linearly separable. Yeah.
Is there a way to take data that doesn't seem linearly separable to begin with and make it linearly separable by applying a transformation?
Yeah, that's a good question. So there is in general ways, like if you use a feature mapping to project into higher dimensions to make stuff linearly separable. I can draw like one example that I thought was pretty cool. So if you had a data set that looked like this, so X's are one class and the O's are another class. There are 2 features here and 2 classes, right? And this is not going to be, just imagine there's enough X's and O's that it's not linearly separable. But there's like a really clever way to define a 3rd feature dimension where if you instead picture the data in 3 dimensions, it's going to become linearly separable. So does anyone want to take a shot at what that transformation might be? Yeah.
It's like a polynomial centered at the origin and
Yeah, essentially. So we want to intuitively, like, there's this circle that's going around, and we want to separate things that are within the circle and outside of the circle. So if you define your feature set to be x1, x2, and x1 squared plus x2 squared, what we're doing is we're lifting the points onto a higher dimensional subspace where things are actually linearly separable. So the transformation that's going on here, I'll try to draw it here. Is the x points are going to end up around here, and then the O's are sort of forming a circle. Like, you can imagine sort of an inverted cone shape where the x's are on the bottom half of a cone and the O's are at the top half of the cone. And once you project things into this higher dimension, it's going to become linearly separable by a plane that cuts between the O's and the x's. So this is pointing to the idea that eventually we definitely do want to be learning non-linear functions, because this sort of data set can potentially be something that we see. But if you just use linear features, there's no good way to learn that data set directly. And one note of historical importance is there is something called the perceptron algorithm, which is also able to handle linearly separable data. It's more of historical importance because people were pretty excited at the time that the perceptron algorithm worked, but we're not going to delve into the details here. Okay, let's go ahead and just jump. To review later, you can go through some of the questions, and the answers are on the slides later on. We'll go ahead and go straight to setting up logistic regression for now. So when we have data that isn't linearly separable, what we're going to do is we're going to define a loss function, and then we're going to try to find weights that minimize the average loss over all the training examples. It's the exact same setup as linear regression. And the first intuitive loss that you probably want to try is like the 0-1 loss. So the way the loss is going to work is the loss is going to take in our prediction and the target variable. And it's outputting how unhappy we are with the prediction. So the way the 0-1 loss function will work is if the prediction is the same as the target, we're going to say there's no loss. If it's wrong, we're going to say there's a loss of 1. And this is sort of natural because if you average the overall losses, you'll get the misclassification rate. If you take 1 minus the misclassification rate, you get like an accuracy on how well you're doing. And that's usually actually the primary metric we care about. But there's some problems with this loss function, mainly in that it's really difficult to actually optimize this objective. To see why that's the case, if we want to minimize the loss function, we have to set the gradient equal to 0, right? But the problem with this is the gradient is actually 0 almost everywhere for this loss function. If we picture the loss function, the gradient is 0 when it's 0 when the z is greater than 0, then the gradient is 0. And when z is less than 0, the gradient is also 0. Because the gradient, remember, is just the local approximation of how the function is changing at a given point. And then between, like at 0 itself, it's actually undefined, right? Intuitively, you can sort of see this as there's this infinite slope. It's discontinuous at z equals 0. So the problem is, if you try to define this loss function and compute updates with your optimization algorithm, you're not going to be able to make any progress because small changes aren't going to lead you anywhere. So Does it make sense of why the 0, 1 loss function doesn't work? Yeah.
If you were to try to recreate the zero loss function with like a Fourier estimation, would the problem still be the same?
I don't know how you would do the Fourier estimation.
Like essentially recreate the graph rather than making it discrete, make it like
Oh, like make it more continuous.
make it more continuous.
Yeah, that's sort of the solution we're working towards. Yeah, yeah. Okay. So let's look at a second attempt. So since linear regression worked pretty well, maybe we can try to just use the squared loss as well for logistic regression. So what we do is we have our targets, which are either 0 or 1, and then we want our predictions to match the targets with a squared error loss value. And then at test time, what we do is we just threshold our values at something like a half, and then we treat our targets as continuous values during training. So this turns out to have some problems as well. And the way to conceptualize why that's the case is if you visualize a data set here. So the pluses and minuses are data points. We have a greater loss for z equals 10 than for z equals 0, which seems pretty problematic. So z equals 10 is in general saying something like we're very confident in a prediction. And this should be a good thing, right? But the penalty is how far away you are from the blue line. Like the blue line is where the loss function wants you to be. But because our target is actually set to be, our goal value is z equals 1, if you predict something really confidently, it's going to have a high penalty. You'll actually have a greater loss for z equals 10 than z equals 0. So predicting the wrong class has a lower loss. So the main issue here is that this loss function does something weird when you predict with high confidence, even if you're correct. So the squared error loss function doesn't quite work as well. So the third choice, which we just alluded to, is rather than have unbounded values, we sort of want to squish all our predictions to be between 0 and 1. And that sort of gives us a notion of a probability distribution that's more natural to work with when we're dealing with classification, right? So the way we squish our values to be between 0 and 1 is with something called the sigmoid or logistic function. And this function that's just pictured on this graph here. I guess key values to note are sigma of 0 is going to give you 1 over 1 plus e to the minus 0 is also 1. So sigma of 0 is 1/2. And this is always bounded between 0 and 1, which is a pretty nice property to have if you wanted to emulate a probability distribution. So when z is really, really big, it approaches 1. And then when z is small, it's going to approach 0. So there's some natural symmetry that goes on around this center point here as well. So the way the logistic function is going to work is we're going to make our prediction. So z is our prediction. But z is in general unbounded, right? And we're going to squish it to be between 0 and 1. So we apply sigmoid here. So squish is between 0 and 1. And finally, we can apply a loss function that measures the difference between our 2 points. But there is actually like one final step we have to take to get the full-on logistic regression objective. We're most of the way there, but the final cost here still has a small issue. And the main issue is like, this is the gradient. Actually, let's go back to the slide. Are there any questions on the logistic regression, logistic function itself? Okay, cool. So the problem that arises when you just use the mean squared error with the logistic function is, let's say that t equals 1, so our target value is 1, and our prediction is really wrong, so we predict y equals 0. The main issue is that the gradient is actually going to be pretty small here. So in order for our problem, in order to actually make progress on learning the actual function, we want to take a large update when our predictions are really wrong. But if you use the squared error loss function and compute the gradient with respect to the weights, we can apply the chain rule. So we take the gradient with respect to our prediction, and then the gradient of the partial derivative of the prediction with respect to the weights. The main issue is the partial derivative of the loss with respect to the prediction is really small here. So this is approximately 0 times some other value, and that's going to be pretty close to 0. So the main issue here is, even if we are very wrong, the updates are small. So there's just like one final fix to apply, like we just want to change the final loss function, and then we should be good to go with the logistic regression function. So hopefully this sort of motivates the design decisions we make along the way, because I guess when I first learned this, it was just sort of pulled out of thin air, and this shows like why other natural definitions are quite incorrect. Yeah.
So the goal would be to make it more of a convex shape?
Yeah, exactly. We want a convex shape where the penalty is greater the more wrong we are in our prediction.
But still bounded between 0 and 1.
Yeah, we want our prediction to be between 0 and 1, but the loss can potentially go much higher. Yeah. So the final step that we'll arrive at, and there's no more modifications we make after this, is something called the cross-entropy loss. And the cross-entropy loss is defined in the following way. There's sort of two definitions depending on which of the two classes you're predicting, and it's penalizing how heavily wrong your prediction is. So if our target class is equal to 0, it's going to be equal to minus log 1 minus y, which on the plot looks like this. So this is a function that's pretty well behaved because it's convex, it's continuous, and it's also smooth, which means the gradients are nice. And it has this nice property where it's 0 if our prediction is perfectly correct, and it's going to scale up as the more wrong our prediction is. The flip side of it is if t equals 1, we're just sort of flipping it around this y equals 0.5 line, and the same description I just had holds, it's just the other way around. So that's how we define the cross-entropy loss. For notational convenience, you'll often see it written in the second form, where essentially the second form collapses into the first form. So if you sub in t equals 0, this first term goes away, and if you sub in t equals 1, the second term goes away, right? So depending on what your target is, you can write this whole thing in one single expression rather than as a conditional expression. Yeah.
T would be the label.
T is a label, yeah. Yeah.
So if you classify something as not, or like if you classify something as spam, that would be t is equal to 1. But if you classify as not spam, it would be t equals to 0.
Yeah, exactly. Yeah. Right. Yeah, hopefully this notion of like how wrong you are should make sense, right? So like if you're forecasting an election or something like that, then you should be penalized much more heavily if you say you're 99% confident and you're wrong versus if you're 90% confident and you're wrong. Any other questions? Okay. All right, so this is the final setup we have. We first make our, we first form this linear, do this linear dot product to compute the z's. The z's we'll actually also refer to as the logits, because they're sort of analogous to, I guess it's just the term we use for what the z's are. And then we apply the sigmoid activation function to get the y. And finally, we compute the loss function between t, which are the targets or the labels, and the our prediction y. And then we can take our gradient steps. This picture here is just saying asymptotically it's going to approach this curve here. All right. So I guess one other thing to note here is, in general, when we write this loss, cross-entropy loss, and sum it over all our examples, there's no closed form solution. So it's unlike linear regression. Intuitively, it's because it's not linearly separable, there's no actual way to minimize the loss perfectly or like get close to perfect. So that means we have to rely on iterative methods like gradient descent to tackle this objective. So we're gonna go ahead and, like, in general, initialize our weights to some random distribution and then take steps to update our weights over time. Okay, there's a numerical instability issue that we'll talk about. This is something that can occur in your code that can be sort of hard to catch. And the reason this occurs is because we're taking the natural log of a particular value. If it's small enough, it can cause numerical issues. Like, you might have encountered this if you take log of a really small number. Initially, it's going to be negative, but after a certain point, you might get a round-off error, like it becomes a positive number, or it's like close to zero. But luckily, there's like a good way to get around this. The key is to use something called the logistic cross-entropy function. So you can think of this as it's just condensing the final two steps of our procedure into one single step. So it's doing the sigmoid of z and the loss cross-entropy in one step and writing it into one single equation. And you can also do this in a potentially vectorized form in NumPy as well with the log add exp function. So this is just something to note when you're implementing logistic regression. Okay. And this is a picture we saw before where you can draw out what the different potential loss functions look like. The final function we arrived at, the red curve here, again, is convex. So there's actually just going to be one global optimum. Okay. So this is the same procedure as before. Like we talked about gradient descent last lecture, and at the start of this lecture, we're just going to initialize our weights, usually at 0, and then just repeatedly apply gradient descent. Let's work through a little bit of the gradient. So something that's a little bit trickier here, I guess, is because there's a few more steps in our computation, we have to apply the chain rule to get the gradient with respect to the weights. So the weights are the parameters that we actually want to update and what we use at test time, right? So our goal is to get weights W, which minimize cross-entropy loss. But in order to do that, it's a little bit tricky, right? Because the weights affect our predictions, Z, which affect the soft version of the predictions, Y. We apply like the sigmoid function. And then finally, the Y and the T come together to define the loss cross-entropy. This sort of computational graph is something we'll draw more in when we deal with neural nets, but this is sort of a simple version we deal with right now, like relatively simple, I guess. And to actually compute the gradient, we have to apply the chain rule. So taking the partial derivative of the loss with respect to the weights, we have the product of 3 different terms. And maybe I'll just go over how these terms come about. So if we look at this term here, partial z, partial wj, it's going to correspond to this xj term here. And hopefully that makes sense, right? Because z is the dot product between w and x. If we're looking at how z changes with respect to wj, it's just going to be exactly xj, right? This term here is something that's a little bit more involved. So this term here is saying that we want to find how y changes with respect to z, and then you have to use the quotient rule. So it's a little bit more involved, but you should be able to do it using what you know from single variable calculus, and it should be derived in the lecture notes as well. And finally, we have the first term, which this first term isn't too bad. If you look at this expression here, when you take the partial derivative with respect to y, derivative of log of y is 1 over y, right? So that's how the y comes out here. So as an exercise, it's probably good to check with yourself that each of these partial derivative terms makes sense later. So in the end, we'll end up with this single update rule here, where in a non-vectorized form, we can write it as this equation like this. Any questions here? Okay. So one thing you'll notice is the update rule that we end up with eventually for linear and logistic regression look really similar. Like if you write it out in terms of the final predictions, the form looks almost identical, and that's not entirely a coincidence. They actually turn out to be part of a larger family of models referred to as generalized linear models, which we won't discuss in further detail, but there's just a general function class where our updates will always turn out nicely in this form. Intuitively, this is pretty good to have too, because this first term is sort of measuring how far off our prediction is. And then the second term, you can think of it, it's just the row of our data matrix, right? So this is saying something about how if we're really off in some of the predictions and we want to take larger updates corresponding in magnitude to how big each of the data entries are. Okay, let's test our understanding, try to, I guess, tackle some of these harder questions. Yeah. I guess of the questions on this page, are there any that you all want to discuss together, or should we just leave it as review exercise for later? Yeah.
Oh, why did we try cross-entropy next?
Oh, okay. Why did we try cross-entropy loss next? So, yeah, I guess that's the step that we sort of pulled out of thin air a little bit. Like, there's different potential loss functions you can choose, but we in general want a loss function that's convex and continuous and penalizes wrong predictions more. cross entropy is a loss that does all of this, and the generalization to the multi-class problem sort of follows really naturally from the cross entropy loss. Yeah, go ahead. Question.
What does cross entropy have to do with centricity?
Yeah, that's a good question. I'm not sure if there's a direct connection. I guess both have log terms. Oh. You can potentially think of it as a divergence measure between uniform, like a one hot distribution and this probability distribution you predicted. So I think there is like some information theory way you can interpret the cross entropy loss term. Okay. All right, so I guess to check your understanding, you should work through these questions later just to make sure you understand the different concepts. Let's jump ahead to linear classifiers versus k-nearest neighbors, and then we'll circle back and talk about finite differences next time. Because I guess now we have two different classification algorithms, nearest neighbors and linear classifiers, and it's potentially useful to think about some of the ways they're the same or different. So the decision boundaries end up being really different. So for linear classifiers like logistic regression, you end up learning just a line if you're not doing any special sort of feature mapping. But for k-nearest neighbors, because of how it's defined in terms of other data points, we end up with this potentially jagged decision boundary. Let's try to list some of the trade-offs between the two algorithms. So I guess, what are potential benefits or drawbacks of each of the algorithms? Yeah, go ahead.
They're simpler to implement than k-nearest neighbors?
I guess it depends on what type of algorithm you prefer. Like ease of implementation could go either way. Like some people may argue k-nearest neighbors is easier because you're just searching through your data set for whichever points are closest. Yeah.
I believe nearest neighbor is more limited, but linear classifiers is more inclusive in terms of data points, right?
What do you mean by more limited?
Like nearest neighbor, you only look into like the nearest neighbor.
Right, yeah.
To decide like whether your data point is valid or not, right?
Right.
Linear classifiers is more inclusive. You collect more. There are more factors into it, right?
Right, yeah. When we're making a prediction, we sort of accounted for all the other points rather than just the k closest points. So yeah, I guess that is a potential advantage for linear classifiers in that it most likely scales better to higher dimensions. There's two other things that pop up sort of, right? Like the time and memory complexity. Yeah, did you want to add?
Linear classifiers have faster test time complexity.
Yeah, exactly. So linear classifiers are faster at test time. And I guess in terms of how much data you store, it's k-nearest neighbors has no training time. Like we don't have to run gradient descent or anything to do k-nearest neighbors, but you also have to end up storing all the data points. And yeah, I guess there's probably a few more trade-offs we can discuss, but these are just some to get started. And yeah, we can pretty much leave off here, I guess, and circle back to the rest of these later on. Are there any other questions before we wrap up?